Dear girls, in this session, we are going to see advanced SRAM designs. So, when we consider advanced SRAM architectures, we have to majorly consider what type of technology with which it is designed, what are the parameters it is to be taken consideration for the performance betterment, and what are the companies that are coming with the advanced architectures we have to observe. So in this session, we are going to see 1 MB SRAM to 4 MB SRAM designs initially. Then it will be extended to 16 MB SRAM design also by the companies. What are the companies? We will come to know. So here, basically, the advancement can be seen in terms of technology node, first of all. Technology node in the sense channel length. So effective channel length, if you reduce effective channel length from one measurement to other measurement, the size of the channel length reduces, it results in less size of the complete device such that number of cells can be more, cells can be incorporated within the given area, so the density will be increases. So, so that is the first one. So shorter gate channel length is the first parameter to see the advanced structure. The very first parameter to be considered as shorter gate channel length is also called as effective length. Is also called as feature size. So that is quite linearly into faster access time. So whenever you reduce the channel length, obviously the carrier will take lesser time to cross, as the carrier's crossing will gives you the current conduction. So the memory cell can be accessed very fast. So that's why shorter length leads to a fast access time. So that is first parameter. Then the other way to achieve higher density memories is by scaling down. So scaling down is another possible way. Scaling down in the sense technology nodes 180 nanometer to 90 or 60 like that. So scaling down is not only cell area, but around the cell, what are the peripheral components which are connected, their widths or their areas or the connecting wires and all also can be reduced. So generally, if you observe that the cell area itself is taking more than the place within within the wafer. I mean to say 50 to 60% area of SRAM is the memory array. So remaining 40% will go for the connection of peripherals like column decoder or array decoder or other sections. So 50 to 60% 50 to 60% area is required within the wafer for the sake of memory. So here, the problem of reducing chip size directly relates to the reducing the cell area. So in order to reduce the cell area, we have to look into the entire peripheral circuitry also, how much parallelly it could be reduced, as well as what is the total area occupying the memory. We have to observe. So here one example is seen that the cell size of a function of SRAM density can be seen such that here in this graph. So this is the graph shows the density. So 64 kilo size of the memory to 256 megabits of size of the memory is considered. 64, then 256, 1 mega, 4 mega. So then density is increasing. Density is increasing in the sense number of cells which are incorporating 256 mega bits of memory is considered. So those many cells are considered, and if we observe the cell size, so 64 kilobits the cell size was occupied in such a way that this is between 100 to 1000 micron meter square. So cell size is around, say for example, this is some 300 400 range. So that 300 400 micrometer square range is reducing if you observe that 4 mega bits of memory. Similarly, 64 bits of memory, it come down to between 10 to 1. Say for example, 8 micrometer square chip area. Then this one also, that is cell size, sorry. So that is also, even if you go for 256 megabit memory, the cell size is reduced even nearly to 1 micrometer square. So you can imagine how much the cell size is reduced, how much the effective length is reduced accordingly. So this graph is very much important. as the technology is growing, we can observe the reduction in the cell size. So that is where the major concern, the cell size with the technology as well as scale down properties, then shrinking the line width, the peripheral circuitry which are connected using lines, lines of metal or lines of copper or whatever the lines which are taking peripheral circuitry, shrinking line widths and a variety of process enhancement. So this shrinking length is another parameter to take into picture for the advanced memories. Another one is variety of process enhancements. So for the process, we may use CMOS process, or we may use technology of 0.5 micrometer, or we may use by CMOS, we may use the other process like mixed technology. Like that, the process is also one important major parameter in order to observe that advanced memory. So these are the responsible parameters. The one is channel length, the other one is scale down, the other one is shrinking line width, that is peripheral circuitry, then variety of process enhancement. All these four parameters are responsible for density and performance improvement. This is very much important point also. Responsible for density as well as performance improvement of advanced memories. So now people earlier were used polysilicon load resistors. Generally, SRAM is consisting of transistors for four transistors. Four transistors are for two access transistors and two are device NMOS transistors. And the load transistors are earlier people have used in the name of load transistors polysilicon load resistors. So later on, the polysilicon load resistors are converted into PMOS transistors, replaced with PMOS transistors. That is completely CMOS in CMOS SRAM structure. So earlier, as PMOS, polysilicon load resistor were used as load, so that was very much good for 1 MB SRAM designs. But when it goes to 4 MB or above that range of memories, the polysilicon inherently gives a higher resistance. So it needs more voltage to operate or to access the transistor. So more voltage is required to make the transistor on. So as polysilicon resistor is more, it is very difficult to achieve high speed operation for the higher memory density SRAMs. So that is where it is very challenging for building of 4 megabit or above SRAM cells. Then people have identified that the resistance must be small enough to provide sufficient current to the storage node. So storage nodes are like Q and Q bar are the storage nodes of the cell. So the resistance should be as much as less such that the capacity will be more as well as more higher dense ramps can be built. So that's why this is one example shown on the left hand side for four transistor SRAM. As I mentioned, the two access transistors and pull down transistors are two more. So including this access transistors and pull down transistors are totally four transistors, and the load devices are resistances. These resistances are nothing but poly resistance. The poly resistance in the fabrication, if you observe that, it requires a doped region, left hand and right hand side a doped region, and in the middle if you observe that it is a load resistor. So this is where the poly resistor fabrication have been taken, and this is a mask too. This mask too is actually the region where the resistance region is required. That region will be masked with the mask layer. Remaining two are given for the doping. So the intermediate region resulting in polysilicon resistance that will be used as the resistor's load. So this is a picture for polyresistor, and this is the picture for transistor SRAM. So people have identified the drawback that polyresistor having higher resistance cannot be useful for building the higher density of SRAM. So people have tried with the alternative, that is CMOS. CMOS, in which these load resistors are replaced with PMOS transistors. So in the CMOS, two complementary transistors will be seen, that is PMOS and NMOS. So R load resistors, that is the power supply of the memory array, is zero point 0.5 to zero point 0.6 micrometer technology has to be less than 5 volts. So this is one more factor to replace these poly resistors with PMOS transistors, is that this kind of design requires 5 volts. This kind of design cannot be suitable for the technologies with less than 5 volts. And it's also the technology dependency, that is zero point 0.5 to zero point 0.6 microammeter technology, and it requires a power supply 5 volts. So even though the external chip supplies 5 volts is maintained also, that is the design R load cell is 5 volts is required. So that's why an alternative approach is 4MB generation as a development is a 6 transistor cell with 4 NMOS transistors. So that 4 NMOS transistors in the silicon substrate and 2 PMOS load transistors. As I mentioned that in the CMOS, that is 2 PMOS load transistors will be used. Formed in the thin film polysilicon layers above the cell. So these load resistors are replaced with the PMOS transistors, and the technology we used was thin film polysilicon layers. So above the cell, that is actually 1 MB SRAM. See here in the advanced memories, what are the companies with which, what are the types of memories we are discussing is, here I mentioned as a name besides to that, that is ABC. I have given a name in such a way that it is the company developed, that is NEC company in 1988 developed an SRAM, 1 megabit SRAM with the technology zero point 0.8 micrometer technology, in which it was used PMOS polysilicon for the load devices. So SRAM employed the P-channel polysilicon resistors instead of poly resistors. So this vertical, at the same time, it was used stacked the N-channel driver transistors. So whatever the driver transistors, these are driver transistors, right? N-channel driver transistors above which PMOS will be seen. So these N-channel driver transistors are used as stacked channel driver transistors. So stacked in the sense one above the other, one above the other. So this vertical cell offers size benefit. So when the NMOS transistors are stacked together, the size of the complete SRAM reduced. So that is another advantage. This vertical cell offered the size benefit of the R load resistor cell and the noise margin of the 6 transistor cell also. So 6 transistor cell, when we use PMOS transistor, noise margin is improved, as well as comparatively R load resistor process also complexity reduced in the case of PMOS load. So here this is one example shown here, thin film stacking. So as I mentioned that 4 MB is higher density SRAM compared to 1 MB, where 1 MB is designed with a poly resistor as load device. When it comes to higher design or higher capacity memories 4 MB, it was designed with PMOS as load resistor. Carefully see the difference. 4 MB uses PMOS as the load device, 1 MB uses poly resistor as the load device. Okay, so here 4 MB having higher density because of the advantage of stacking. So here in order to maintain the low standby current, in order to that means standby current in the sense whenever one cell is operating, another cell is in the standby, that means maintaining a low amount of current, right, low amount of current. So there it has taken an advantage of stacked CMOS SRAM cell with polysilicon thin film transistor load. Excuse me. So this is what stacked CMOS SRAM cell with polysilicon thin film. So if you observe that a green color portion is a base, above which a light yellow color, a small portion, the internal portion, if you observe that it is a polysilicon. Once again, one more layer of other layer is taken, that is a kind of silicon again. So like that, one layer by layer, layer by layer, polysilicon is stacked. These polysilicon also, excuse me, these polysilicon also taken like a thin film. That's why this technology is named as thin film transistor load. It is developed in the stacked CMOS SRAM cell. So this polysilicon thin film transistor TFT load device, this behaves like a load device. So given an advantage of increasing noise margin, as also space reduction, right? At the same time, the off current and on current of the TFT load are very much important. So what is the amount of current it is taking for a cell to for a transistor to on or off? That minimum amount of current is required in such a way that, or the reduction of the amount of current is required in such a way that the speed of the cell will be increased. Okay, important parameters to reduce the standby current and increase the noise immunity as well as speed of the device. Right, the special solid phase growth SPG technique. So this, in order to achieve this TFT load, the process used is a special solid phase growth. Okay, and at the same time, three-level polysilicon technology, the fabrication of the cell is based on three levels, which are one level is based on three steps, which are three-level polysilicon technology. Then in the three-level polysilicon technology, first poly is meant for used for gates of the access and driver NMOS transistor. So here, for the fabrication of TFET, we require a TFET, we require three-level polysilicon technology. The three-level polysilicon, that means polysilicon is stacked, we just mentioned, no. So first layer of polysilicon, that first layer of polysilicon is used for gates, gates and access transistor, driver and mass transistors. So gates of the access transistors, driver transistors. The access transistors are connected to the bit line, driver transistors are connected to the inverter pull down material. So gates of the access transistor and driver and mass transistors. And for the VSS line, so this is the first polysilicon connected to all these. Right, the second polysilicon layer for the gate of the TFT load. So TFT load is the top layer compared to the first level poly. So TFT load device is there, no? So the TFT load for that this second poly will be connected. And the third poly, so above this second poly, third poly will be layered. The third poly layer, that is where we can see active layer of the TFT load and VCC line will be connected. So the TFT becomes the load device now. That will be connected to the, just like a PMOS transistor, how it will be connected to VDD. In the similar way, this TFT load, the third polysilicon will be connected to TFT load and supply VCC line. So the same structure can be seen here. So this is the N substrate, above which P well, then above which, if you observe that these are the N plus material, N mass FET here, and then above which one third poly, and then beneath, this is the top layer of third poly, beneath that you can observe that second poly, beneath that you can observe that first poly. So this is first poly, little bit wider than second poly, and this is little bit less wider compared to first poly, then third poly is little bit less wider compared to second poly. So like that you can see the stack of polysilicon layers in order to achieve the complete SRAM. Um, then here the figure is showing CMOS, stacked CMOS SRAM cell, schematic cross section as well as layout also. And basically before going to the layout, let us revisit the parameters which are required for a upgradation of memories, like advanced memories. What are the parameters are essentially to look into? So first parameter is size of the memory. So size of the memory is 1 MB or 4 MB or 16 MB, like that. What is the size of the memory that is to be fabricated? Then what is the process technology that is to be taken for the fabrication, like 0.5 micron meter or 0.8 micron meter, like that. Then number of poly layers. So as just now seen that three poly layers are seen in this 4 MB SRAM construction. So like that, how many number of poly layers are it is taking? Then at the same time, type of load, whether it is as in the case of 1 MB, we have seen resistive load or PMOS transistor as load or TFT as load, like that. The type of load is also concerned, and then memory cell area. So here, if you observe that the construction of this CMOS, right now, what is the process you have taken? So that is taken the cell area of 17 micron meter square. So in the case of 1 MB, the cell area is taken is given as the cell area is given as, in the case of 1 MB, in such a way that it is uh, 12 micron meter square, if you observe that. So like that, what is the cell area it is taking? Then performance parameters like what is the standby current? That means when the cell is in the off condition, how much current it is able to draw. It should not be more. Standby current should be very less, as less as possible, and the access time also important, right? Standby current and supply voltage. So how much supply voltage is required for it? Whether it is 5 volts or 3 volts or more than that or less than that. So supply voltage, then typical memory access time. As just mentioned that as access time depends on the amount of current that is drawing while writing the data or reading the data. So access time. So and then low voltage operating capability. How far we can reduce the voltage such that the cell information will be written or retrieved. So that is a low voltage operating capability. So all these parameters are important for observing the upgradation of memory technologies. So nowadays, technologies are very much advancing with the TFT technology or any other process technologies. The latest papers you can go through. There are so many papers are evolving. So latest papers you can go through. I have pasted some of the two links here. I will show you them. So here in this case, this Hitachi company, whatever Hitachi company constructed with 0.5 micron meter process, observed with cell area of 17 micron meter square. Then the standby current is of 0.2 micron amps, and then supply voltage it is operated with the supply voltage of 3 volts and access time of 23 nanoseconds. So here this cell is represented in the circuit diagram representation. If you observe that this is TFET, the load devices are TFET, and then access transistors are access transistor as well as pull down transistors are NMOS, and this is just simply like a CMOS transistor how we have seen in the very first classes. Then this is the corresponding layout. So Q1, Q2, Q1, Q2 are the node of a cell. So Q1, Q2 are which are the down transistors, which are nothing but NMOS transistors. So these Q1 and Q2 are the NMOS transistor node points, and at the same time Q2, Q3. This is Q1, Q2, then Q3, Q4. Q3, Q4 are the access transistors, and Q5, Q6. Sorry, Q3, Q4 are the PMOS transistors. PMOS is nothing but here TFET. So TFET transistor construction Q3, Q4. Okay, this is Q3, Q4, right? Then Q5, Q6 are the access transistors. This is Q5 and this is Q6. These are the access transistors. And these two light colored lines are VCC and VSS. And wherever this transistor, polysilicon, and diffusion of TFET and diffusion of NMOS transistor to be connected, their metal is taken out, and this metal is lightly colored shown here. This is right logic line. Is also between this Q3, Q4 and this diffusion line, it is taken out. Okay. Sorry, polysilicon line is connected with the metal. That line is taken out with the right logic line. Okay, light colors are the connectivity which are from the process, as the TFET process is different, NMOS process is different. Directly we cannot join. So metal is required for the joining. So from the joining point we have taken out right logic line. Okay. So this is the right logic line. Access transistor one line we have drawn, no right logic line or word line. This is the metal line actually. So from this is extended from this joint point. Okay, this is the layout. Now here this layout is also represented with a new technology like a staggered three-dimensional 60 SRAM cell with independent double gate transistor. This is actually taken out from one paper in which vertical slit FET was used. So here, if you observe that this is the base, this is one interconnect layer. This gray color is a metal. One interconnect layer above which one more layer of the transistor, and this is one more like that. The vertically it is stacked up. So this is layer one. VS FET layer 1, then interconnect layer 2, then VS layer 2. So these intermediate one are VS FETs. In between interconnects are connected one after the other, just like a building of an apartment floor by floor. Okay, so here these kind of advanced memories will be used, varieties of memory, what do I say, decoders. So at the same time, these advanced memories is also reduces the error, any error prone designs also. So these kind of advanced memory cells have excellent soft error immunity. That means soft error in the sense writing of the logic one, reading of the logic one, so that is very less amount of values of voltages rather than compared to supply voltages. So whenever any data is writing, how much is the supply voltage, that much will not be used for writing. So the reduction of the voltage may cause sometimes errors. In the previous technologies it was so happened, but when it comes to advanced memories, the reduction of the even minute values of voltages also, it can be capable to take out the exact value while reading. So that is what soft error. Soft error in the sense, when you are writing a data, if you do not retrieve the same value, it will be the error, right? So soft error in the sense, reading the data, it will not be, if it is not perfectly read whatever the amount of voltage, then there is an error will be represented. So reading and writing error, if at all comes, so that is what soft error. So those kind of soft errors can be eliminated with the advanced technologies. With the advanced technologies. So these advanced technologies are very immune for the soft errors, and at the same time they have low voltage operating capability. Advanced technologies are like, just now we mentioned, no, that is point 5 micrometer technology with 4 MB with the TFT load. These are all comes under advanced technologies only. And at the same time, these advanced technologies are also using one type of decoders, such as fast sense amplifier circuits, as well as decoders also. So sense amplifiers also to be modified in such a way that it should capture the written value as well as to write the value. Sense amplifiers must be very fast to act there. So fast sense amplifier circuits were used to reduce access time. So this is another modification is required when you construct advanced memories. At the same time, a noise immune data latch circuit was used. So, data before sitting into the memory or accessing the memory, latches or buffers will be used around the memory. So, those buffers also noise immune data latch. That means only the cell value will be retrieved or placed in the cell. The other kind of noise, like thermal, due to thermal conductivity or due to any other movement of the electron or movement of the data, that causes some noise. So that noise also will be eliminated in the advanced memories. So noise immune data latch circuits were also used to get a low active current of 5 milliamp at an operating cycle of 1 micron second. So this is how much advanced the technology you can observe. At the same time, there is an change in the decoders also, a quadruple array word. Quadruple. So that means these decoders, array word decoder. Decoders generally we observe that 2 by 4 decoder or 3 to 8 decoder, generally a direct connection from 2 input to 4 output or 3 input to 8 output connections. But here quadruple in the sense, the structure of the decoder is used in such a way that the minimal input array will be, the minimal input array will be with one size, then output, whatever the input size, that much is output size, but in a stacked manner. That means if you observe in the diagram, I kept one diagram here. So this is one window of the first output. The same second window, if you observe that, that means if at all, if I write a data at one cell, that one cell will be exaggerated to the entire window. So second cell will be taken care with the second window. Like that, the decoder within the given structure, the windows, one window to other window, instead of considering the decoder completely from line by line AND gates or line by line AND gates, which causes more area to occupy. But here, one after the other, the array windows are connected in such a way that it will be taken very less area, as well as resolvement of each window accessing is happened by intermediate sub windows. So for example, in order to access any cell from this window, I can take the input in such a way that this input will resolve which corresponding the outcome should go, or which corresponding output should be given an output that will be resolved using intermediate connecting window. So like this is one example for quadruple decoder, and this is also captured from the latest paper. So such kind of advancement we can see in the latest memories. And here quadruple architecture of quadruple decoders were used with word decoders for four memory subarrays are laid out to one in region. Similarly, this architecture drastically reduces the word decoder area as well as achieving a small chip area of 122 millimeter square. So that is second kind of technology, Hitachi by Hitachi company. First one is NEC company. The third one, advanced memory, when we talk about, that was developed by Mitsubishi company, that is introduced 4 MB memory. With the technology of zero point 0.6 micron meter, but it used CMOS SRAM fabrication. Okay, so it is also used quadruple polysilicon polysilicon. In the case of Hitachi, we have used three-layered polysilicon, but here in this case, Mitsubishi company used quadruple polysilicon. That means four type of polysilicon, including polyside, double metal, pinwell, CMOS technology. Okay, so this is one structure where you can observe that 4 MB memory fabrication. So this is gate like first aluminum, then this is third poly, and the fourth, this is third poly beneath the fourth poly. See, this is the top layer, that is the fourth poly. This is high resistive load, and beneath that you can observe the third poly. So interconnection, this poly will be used as the interconnect, and then there is a contact pad also, and the second poly. So beneath the third poly you can observe that second poly, and then beneath that you can observe that first poly used as a gate electrode. So all these like a stacked polys once again will be seen in this Mitsubishi SRAM. Okay, so overall, if you see process and device parameters to concentrate from one type of memory to other type of memory, advancing from 1 MB size to 4 MB or 16 MB, majorly the technology is the first one to look into. So here, this Mitsubishi is concentrated on zero point 0.6 micron meter with the technology fabrication is CMOS. Then at the same time, N substrate, and then twin well, quadruple, polysilicon, double metal. This is the entire process, the way how to represent a process synthesis in this way. And the design rules which are used for this construction are zero point 0.6 micron meter. Then transistor size is zero point 0.6 micron meter to zero point 0.8. That is NMOS have taken zero point 0.6 micron meter, PMOS have taken zero point 0.8 micron meter. And thick oxide thickness, that is TOX. So that is oxide thickness. The oxide thickness is the one which is layered above the substrate or above this top layer of the substrate is oxide thickness, that is 50 nanometer. Then overall memory cell is high resistive load, that is R is equal to 10 tera ohms can be observed. That is the high resistance load which is achieved by fourth polysilicon. So this is the process. Within these four statements, the process was explained. So this is the way generally people, for foundry people, observe their processes. Okay. So this is the elaborated SRAM block diagram. So this is SRAM block diagram in which you can observe that write enable buffer, IO buffer, then controller, then Y address buffer, X address buffer, and above which sense amplifier circuitry, above which column decoder, and above which transistor gate. So all these are connected one after the other. Then this is for block 30, block 31. These are repeated blocks, block 0 to block 31, block 31. 4 MB requires these many blocks actually. So block 1, block 0, how it is constructed in the similar way. The block 31 till block 31, same structure will be constructed. And this is routing also, power routing as well as clock routing will be taken in between the cells, that is in between the blocks, right? So global row decoder you can observe here, then subglobal row decoder, again subglobal row decoder. So all these blocks are connected one after the other, layered one after the other. Then this is bitline load, then pre-decoder block selector, above which we can see clock generator, address buffer, and X address buffer. So this is entirely block diagram of 4MB SRAM. 4MB SRAM, which is constructed by Mitsubishi company with the technology 0.6 micron meter. Okay, so and if you observe that each cell size is observed with 3.5 by 5.3 micron meter square. So the memory cell size, right? The memory cell size is 3.5 by 5.3 micron meter square. So the first polysilicon polyside is used for the gate electrode of the transistor. So here we have seen that four polysilicons, no? So first poly, second poly, third poly, and fourth poly. So first poly, how it is used? The first poly, that is also named as polyside, is used for the gate electrode of the transistors. So, first poly is used as gate electrode. Second poly is used as contact pad. Is also used for electrically isolated from the first polysilicide laid over it. Okay, then this results in cell size compaction. So, as this second poly itself is used as isolation in the name of contact pad, the advantage of using the second poly of the same material for isolation from the first poly side. So the material compactness, that means the some complete design compactness is seen here. So cell size compactness is improved. Second polysilicon and the diffusion area are silicided with a self alignment technique. So to reduce the sheet resistance. So this is one process advancement like second poly and first poly. Second poly and the diffusion are aligned such that are self-aligned using self-aligned technique that we already seen in one of the sessions that gate is layered first, then diffusion and source are layered. That is where we can see that gate will be used as self-alignment. For the process of CMOS technology, we have discussed in one of the sessions, earlier sessions. You can go through once again. So the same technique here also will be used for the second poly to first poly. Second poly will be used along with the diffusion area. That is silicide with the self-alignment technique to reduce the sheet resistance. So the third poly is used for the interconnection and power supply line of the memory cell. And finally, fourth polysilicon used for resistive load. That resistive load is of 10 tera ohms to achieve a low standby current. How much is the resistance the layer will offer? Then standby current, that means accumulation of the charges will be eliminated in that way. Okay, so standby current will be reduces. For that purpose, high resistive load will be used. So the bit lines are formed by the first metal with the barrier metal layer, and this SRAM has 20 nanoseconds access time at a supply voltage of 3.3 volts. So previously, if you observe that what are the companies which were designed their technologies, their SRAMs with 4MB, it is 23 nanoseconds access time. It was taken with the Hitachi company. So the access time is reduced in the case of Mitsubishi company SRAM. So that is come down to 20 nanoseconds. So that is where you can see the advancement of memory designs. So memory designs, in order to compare how much access time it is taking, what is the minimum standby current it is giving, what is the cell area, what is the supply voltage it is taking, like that we can compare, and whichever is the better one, the industry people will use that. So here in this case, Mitsubishi company SRAM is using 20 nanoseconds access time at the supply voltage of 3.3 volts, and is also achieved by a new word decoding scheme and high-speed sense amplifiers. It is also has a fast address mode which is suitable for cache memory applications. So this kind of memories once built, they find applications like cache memory. Cache memories are all present between main memory to CPU. So CPU will use the immediate values which are required. It can take from the cache memory. So cache memories are not like a huge memory that will be designed for main memory. So cache memories are very small in size. At the same time, they should act very fast in such a way that to give the immediate data which is required with the CPU. So that much fast device is required between main memory and your CPU. So SRAMs which are used as the cache memories. So these high speed cache memories will be, these high speed SRAMs will be used as a cache memory. So with this, we can end the session. Then we will see 16 to 64 megabit SRAM development in the next session. Thank you.